In this lecture, we're going to talk about acids and bases, and we're going to introduce what acids and bases are in terms of ionic molecules and how their ionic character explains a lot of their properties. Here's some properties of acids and bases that you should know. In general, acids such as lemon juice and other citrus fruit juices are sour tasting. They have a pH that is going to be less than 7, and they turn indicator paper a red color. So this is an example of litmus paper, which is a type of indicator paper most people are familiar with. Bases in general are bitter tasting, such as a raw eggplant has a juice that is very bitter. Baking soda is bitter. They feel slippery on your fingers, almost like a thin, slimy feeling. Their pH is greater than 7, and they're going to turn litmus paper and other indicator solutions blue. So this picture here shows a typical color wheel that comes with pH or indicator paper. And what you would do is you would take the paper, put it in whatever solution you are testing, and it would turn a certain color, and that color correlates approximately to the pH. So whatever substance this paper was testing appears to be about a pH 10. So let's look at what acid and base molecules are. So Arrhenius was a scientist back in the day who proposed that acids are substances with hydrogen and bases are substances with hydroxide. And this was a little limiting because while all acids do have hydrogen ions that they donate, not all bases have hydroxide. So let's look at a more specific definition. Bronsted and Lowry later modified Arrhenius' definition of acids and bases to be less specific and to, in general, look at proton transfer. So they defined an acid as a substance that is going to produce or donate protons. And a base is a substance that can accept protons. And this is when they are in a solution. And this is very similar to Arrhenius' definition because a hydrogen ion is a proton. So if we look at a picture of a hydrogen atom, it's made of one electron and one proton. If that were to ionize, meaning the electron was to leave the atom, all you're left with is a proton or a hydrogen nucleus. So a hydrogen ion is synonymous with a proton. So what is important about acids and bases is in their definition they are talking about ionization or dissociation. So an acid is always going to have hydrogen in it, and it is always going to dissociate to leave hydrogen ions and some other section to the molecule, some other sort of polyatomic ion. For example, hydrogen sulfate or sulfuric acid, H2SO4, when it dissociates, it's able to remove 2 hydrogen ions and leave a sulfate molecule. So these 2 hydrogen ions can then go to any other substance. A base is a substance that may or may not have OH, but regardless, a base can accept a hydrogen ion. So for example, this base, and we might not necessarily know this is a base just by looking at it, but by its behavior we can tell it is a base because we see that it accepts that hydrogen ion. So this hydrogen is added to the NH3, which now makes it NH4 with a positive charge. So the law of conservation of charge applies in this case as well. We have to be very careful to make sure that we are making sure that our cation ions and anions are balanced out. Cn minus we might not also recognize immediately as a base, however it can act as a base by accepting a hydrogen ion or accepting a proton, and in this case it's going to become hydrogen cyanide. So an acid is very easy to recognize because it has these hydrogens in front. However, a base may not be as easy to recognize. Subsubstances can either donate or accept a proton, so what they are called amphoteric. That means both. So for example, water is amphoteric because it can donate a hydrogen ion or it could accept one. So for example, if we have a water molecule acting as an acid, we would see that one of these hydrogen ions is going to be cleaved off, and now we have the hydrogen ion on its own, and the rest of the water molecule that would be left over is OH minus. If water were instead to act as a base, it is going to be accepting a hydrogen ion into it. So now instead of H2 we have H3, and because of the law of conservation of charge it's H3O+. This molecule H3O plus is called hydronium. It is a polyatomic ion that is frequently used when you're looking at acids and bases. This is an important ion to know. Water can also what's called self-ionize, meaning it can ionize itself, and it could be an acid and a base at the same time. So if you have two water molecules, one of which is acting as the acid and the other is acting as the base, and we know this because one of them is going to give away a hydrogen ion, which is the definition of an acid. One of them is going to accept this hydrogen ion, which is the definition of a base. So what we will have left is a water that has gained a hydrogen to make hydronium, and a second water molecule which has lost hydronium and is only left over with hydroxide. So this information is going to be used in a few lectures from now, in where we are going to look at some formulas that are based on hydroxide and hydronium concentrations, and it's based on water's ability to self-ionize. There are two other vocab terms that you need to know when you're looking at acid and base reactions, and that is of a conjugate base and a conjugate acid. When you have an acid and it donates its hydrogen ion, and you are left with an anion, such as chloride. So hydrogen chloride or hydrochloric acid, when it donates its proton to whatever the other substance is, in this case it's water, then you are left with the negative ion. This negative ion could take a proton. The definition of something that can take a proton is a base. So when an acid has lost its hydrogen and what is left over can now accept a base, we call this the conjugate base. A chlorine ion wouldn't normally be considered basic. However, because it comes from an acid and it is in a reaction where we are doing an acid-base reaction, we would call this a conjugate base. The converse is also true, where we have, in this case, water is acting as the base. We know water is the base because it is accepting the hydrogen ion. When water accepts the hydrogen ion, it becomes a positively charged molecule which has extra hydrogens. This H3O hydronium ion, it could then turn around and give away that proton which it just had. A substance that can give away a proton is an acid. So this would be considered a conjugate acid because it has come from a base. So you often will have pairs. You would talk about a conjugate pair. And the pair we see in this example is that the acid pairs with its conjugate base, or meaning the conjugate base comes from the acid. And conversely, the conjugate acid is going to come from a base. So this pair is the base and conjugate acid pair. So in general, to simplify and summarize everything we've talked about so far, in an acid is always going to be some substance A which has hydrogen in it, and that hydrogen is then going to be donated to some other molecule in the reaction. That other molecule is going to act as a base by accepting the hydrogen. By accepting the hydrogen, we now have HX, just meaning generic for whatever the molecule is. And because it can now give away a proton that it has, this is now our conjugate acid. And whatever was left over when the hydrogen left that acid molecule, here we go, is now going to be the conjugate base because it can take a proton. So this is a very easy generic equation that can be used when you want to simplify a problem and you want to get rid of sort of the extra molecules or the extra atoms which are making it confusing. You can just break down an acid and basically symbolize it as H plus whatever the rest of the molecule is. Likewise, you could simplify an equation for an Arrhenius base by using the symbology BOH. B meaning a base molecule which is containing OH. This B could represent anything. If this was NaOH, then B represents the sodium ion. So in this case of an Arrhenius base, you would have base is going to donate the hydrogen ion, or the hydroxide ion, and it's going to donate to the other molecule in the equation. This other molecule is then going to become XOH, meaning whatever generic molecule this is going to have the OH in it, and it's going to be negative charge now. And because it has an OH, it is considered a conjugate Arrhenius base. Then the base, the rest of the molecule that was left over after hydroxide left the base, is going to be left over here. And this is going to be, it could be considered a conjugate acid because it's slightly positive, or it would just be considered the other ion in there. So again, this is an easy way of taking a very complicated, or what could be a very complicated reaction, and you can simplify it. So you will see this as you take advanced chemistry classes, where oftentimes acids and bases are represented with A's and B's.